In this section of the class, what we're going to learn about is the topic of higher derivatives. Up till now, we've taken what we've called, and I really have never called it this before, but we've been taking what we call first derivatives. So I give you a function, and you take the derivative of it, and so you come up with something, and what I haven't told you up until now is that that's actually called a first derivative. It just means that you've taken the derivative one time. Well, as we've kind of alluded to in the first section of the course, you can keep taking derivatives, like if you start with the position function, and you take the derivative, you get the velocity. And if you take another derivative of that result of the velocity, you get the acceleration. So in that case, we said that that could be also called a second derivative. So we've sort of talked about it sort of in a roundabout way, but we're going to work a quick few problems. Not too many, but just a few, just to show you the terminology and just to show you how you write this stuff down. So just recall that the first derivative, whoops, got to spell derivative, right? The first derivative is written like dy dx, which is the derivative of the function y with respect to x, and we also said that you can write that as y with a little prime on it, and that kind of means first derivative. The second derivative, these little lines here mean derivative, you would write as this, d squared y over dx squared, and you would also write that as y with two little primes. So I'm just showing you here the kind of the big picture way that you write this stuff down. Derivative of y with respect to x. In this case, this is telling you it's the second derivative of y with respect to x. Don't ask me why they decided to put the two here and here. I don't know. That's lost in the history of calculus. But this is how you write the second derivative. You can also write it with your variable with the two prime marks to indicate that you want to take the derivative 3 times. The third derivative can be written, as you might guess, d3y over dx squared. And again, these aren't cubes and squares. So this should be a 3 there. This doesn't mean dx to the third power. This is just a reminder to the person that's writing the problem that this is a third derivative. So this is not an exponential. Okay, and you can write that as y with 3 little marks. And also, when you get up, to the fourth and fifth and sixth derivative, putting all these little marks is kind of a pain. So another way you can write it as y with a little parentheses and then a 3 here. Okay. The parentheses indicates as a reminder to you that you're not taking an exponent. This is not y to the third power. This is the third derivative of y. So that's what the parentheses mean. If you were to write it like this, that would get really confusing after a while because, then you might start thinking that you're taking a, y to the third power or something like that. So yeah, you can take infinite number of derivatives. You can keep taking derivatives until you get nothing. And eventually you will, in most cases, do that. So this is the basic way in which you write derivatives. Now we're going to work a few problems to kind of illustrate this in the most general sense. So what if you have f of x is equal to x to the fourth power minus 3x to the third power plus 16x? And the question is find the first and the second derivative of this function. Well, we've been finding first derivatives all day with the single prime mark, and we know how to take derivatives of polynomials like this, so we just do that. This is going to be 4x to the third using our exponent rule. 4 comes out and you have 3 in the exponent, minus 9x squared. The reason it's 9 is the 3 comes out of the exponent. 3 times 3 is 9, and the exponent is 3 minus 1. And then over here you're just left with 16 because 1 comes out of the exponent. 16 times 1 is simply 16, and you have a little x to the 0 power here because 1 minus 1 gives you 0. And so in the end, that drops away. So this is the answer. This is the first derivative of f of x. This is the slope of this curve. So this curve here represents, at any given point, the slope of this curve. Okay? So the question is, what's the second derivative? Well, we write that with the 2 little prime marks like this, the same as I showed you here for the second derivative. And the only thing you have to do here is, in order to find the second derivative, you just look at the first derivative and take the derivative of that. And that will give you the second derivative. So looking at this formula here, let's take the derivative of that. We have 12x squared. 3 times 4 gives me 12. And the exponent is just 1 minus 3 there, or 3 minus 1, minus 18x, because 9 times 2 is 18, and the exponent is going to be a 1. And then here's a constant. 16 is a constant, so the derivative of that is 0. So these are your answers, okay? These are your answers. This is the first derivative, and this is the second derivative. So really, this is very simple, and that's why I'm not going to work too many problems in the section. Get the first derivative just by taking the derivative of your original function. Get the second derivative by just taking the derivative of the first derivative, and that'll give you that. So take the derivative of this to get to here, take the derivative of this to get to here, and you can keep taking derivatives until you're blue in the face. You could take the third derivative, the fourth derivative, and so on. So we're just going to work a couple more problems to kind of give you practice with it. What if you had a function called h is equal to the square root of x squared minus 1. Actually, let's make it x squared plus 1. And the question is, find the second derivative of h. So what you're trying to find is h with 2 little hatch marks here, the second derivative. Okay? Well, the first thing I like to do, as I've been doing all along, is get rid of this radical and write it as a exponent. So when you take the square root, you're raising something to the 1/2 power. Now let's take the derivative of this term here, the first derivative. So h prime is equal to, let's take the derivative of this. We're going to need to use the chain rule, which we've just learned how to use. The big picture here is we're taking something to the 1/2 power, so I'm going to use that power rule. I'm going to leave the inside alone, not going to touch it. The exponent's going to be minus 1/2. The exponent comes out, inside stays the same, and in the exponent it's 1/2 minus 1, which gives me negative 1/2. But I'm not done, because I've got to take the derivative of the inside, which is just 2x. The derivative of x squared plus 1, I think you'll be able to convince yourself, is just 2x. So for h prime, you can see right away that this 1/2 is going to kind of cancel with that 2. It's going to leave you with 1. So that's going to drop away. So really what you're going to have is you're going to have x times x squared plus 1 to the negative 1/2. This is the first derivative. So we've arrived at the first derivative. But the problem wants us to calculate the second derivative. So let's keep on going. The second derivative is just simply the derivative of this, which is the first derivative. So let's do that. Here we have a function of x times another function of x, so we're going to have to use our multiplication rule. And this is going to get a little bit complicated here in a minute, but let's do that. The first term is x, so it's the first, okay, times the derivative of the second term, and the derivative of the second term is going to be negative 1/2 x squared plus 1, and then negative 1/2 minus 1 is negative 3/2, right? Okay. But we're not done yet. We need to multiply by the derivative of the inside here, which is just 2x. So all this should seem very familiar. We did a lot of this stuff a minute ago. So first times the derivative of the second term. The derivative of the second term is this. You've got the negative 1/2 that comes down. You've got the inside that stays the same. You've got the exponent here, which is negative 1/2 minus 1. And then you got the derivative of the inside. Okay. Plus the second term, which is x squared plus 1 to the negative 1/2 times the derivative of the first term, which is just 1 because the derivative of x is 1. So now, in order to move forward, what we need to do is go ahead and just simplify this to get the second derivative. And you can see that this 1/2 cancels with this 2 there nicely, because that just goes to 1. So in order to continue here, I'm going to distribute this x into this term here. And so what I'm going to have is x times x gives me x squared. And don't forget the negative sign that comes right from here. And then on the bottom, you're going to have x squared plus 1 to the positive 3/2. So all I did was move this term to the bottom by changing the sign of this exponent. The negative x times x gives me x squared on the top. And then over here, you have 1 over x squared plus 1 to the positive 1/2, right? And that is essentially the answer. That's the second derivative. I'm just trying to show you the principle here. You take the original function, take the first derivative, simplify it, you'll get this. Take another derivative of that, and in this case we had to use that multiplication rule to take the derivative. First times the derivative of the second plus the second times the derivative of the first. And we had a little bit of a complication because this was the second term. We had to essentially use the chain rule to get the derivative of the second term. But in the end, we simplify it and we get this. Now, you could play around with this fraction a little bit more, and you could get a common denominator and simplify it a little bit more and do that. But essentially, that is the process by which you go on and you take derivatives to get what we call the higher derivatives. And we've already seen kind of a practical example of why you would care about that. The acceleration is a higher order derivative, for instance, of the position function. So we're going to do one more problem here in this section. If you had y is equal to 5x minus 1 to the 1/2, question is, find the third derivative. Okay? Well, let's go ahead and find the first derivative first. We've done problems like this before. We're going to use the chain rule. This is going to be 1/2. Inside stays the same to the negative 1/2. Because I'm basically doing it like a polynomial. So you got 1/2 times the inside to the negative 1/2. But you're not done. You got to multiply by the derivative of the inside, which is just 5. Derivative of 5x minus 1 is 5. Okay? So to simplify this, you're going to have 5/2 times 5x minus 1, negative 1/2. Okay? So that is the first derivative. Let's find the second derivative. That's going to be the derivative of this term, right? So we're going to have 5/2 times negative 1/2. Again, we're going to do the same process again. Inside stays the same, 5x minus 1. Again, we're going to subtract 1 from the exponent, so that's minus 3/2. But again, we're not done. We have to multiply by the derivative of the inside, again, which is 5. So the second derivative is 5 times 5 gives me 25. 2 times 2 gives me 4, and don't forget my negative sign out front. And then over here in the inside, I've got 5x minus 1 to the negative 3/2. And this is the second derivative. So in order to find the third derivative, okay, you do the same thing again. You take the derivative of the second derivative, and you get that third derivative. So this constant, 25 over 4, just hangs out front, no big deal. Take the derivative of this term, it's the same thing. The exponent comes down, negative 3/2. Inside stays the same. Exponent becomes negative 5/2 because I'm subtracting 1 off of that. But I'm not done. I have to multiply by the derivative of the inside, which is 5. So to sum it up, this is all simplified. If you do this math, this 25 times 3 times 5, and negative times negative gives you positive. In the end, you're going to have 375 over 8. 2 times 4 gives you 8 on the bottom. And you will have 5x minus 1 to the negative 5/2. So you start with a function, take the derivative, and you do all that business, and you get the first derivative. Take the derivative of that, gives you the second derivative. Take the derivative of that, gives you the third derivative. And that is the basic means by which you do this. You just have to turn the crank sometimes, and the formulas get kind of more complicated as you take more and more derivatives occasionally. But essentially, that's the big picture process.